Hi AP Calculus students, it's Miss Culver. How are you? Today we're going to do section 1.3c called Limits That Produce a Slope at One Point. Sorry, I'm not going to actually be in the video. You're only going to hear me because I have no one here to shoot a video for me, and I really want to get this done. So you'll be hearing my voice and you'll be seeing me write on paper. Sorry it's so low tech. In a couple days I'm going to be spending some more time with my writing pad and software for whiteboard on my computer and Loom, and so you'll see a little bit more high tech in the future. I just want to make sure that I have time to work with it. So I'm going to shoot a video by writing the 1.3c notes with you hearing me, and then at the end I actually have them written on a whiteboard. I'll show you those notes, and again, if the cat could shoot the video for me, she would, but it's just me. So here we go. If at any point you need to pause the video to write the notes, please do that. So this is AP Calculus. I'll just put APC 1.3, and the title is Limits That Produce a slope, right? We know a lot about slope, but this is going to be at one point. This is, of the three parts of calculus, this is the second part of calculus. And as I may have mentioned in class, the slope at one point would be really useful because it's a rate of change, and it would be nice to know the instantaneous rate of change at that one moment in time, rather than using the slope formula with 2 points and getting an average. This is called a derivative or difference quotient, called a derivative or difference quotient. AP Classroom uses the term AP quotient a lot, and so I want to make sure that you get used to that. So let's begin our notes. So 1A, what is a secant line? A secant line is a line that intersects a curve at two or more points. Two or more, we'll just be using two, but at two or more points. And here's a picture of that. Let's see, I'll make the curve in black. There we go. And I'll make the secant line in blue. So we'll make 1, 2 intersection points, and there is my secant line. And it doesn't matter the order. I'll make it go through the points a little bit better, a little bit thicker line. But notice this could be the point x1, y1, and this could be the point right here, x2, y2. There we go. So what is the slope of a secant line? So here's B. What is the slope of a secant line? Well, it's simply the formula that you have heard forever, M, and we're going to put a little below SEC for secant line, and we call that a subscript. The slope of a secant line is, how many times have you heard this? y2 minus y1 over x2 minus x1. Isn't calculus easy so far? Okay, now, how can we in calculus make this difficult? No, I'm joking. How does that look in calculus? Or, in calculus, how do we write this slope? And I promise you there is good reason for that. And I just want to point out too, when you see strange looking formulas or things in calculus, These are all the things you need to know, all the concepts to get started. I actually promise you in chapter 2, we start using some very simple, easy rules that come from these harder concepts. So don't worry, it's actually going to get easier. So let me go back. Here's the slope of a secant line, y2 minus y1 over x2 minus 1. X2 minus x1, or in calculus, this is what it looks like. I'm going to do this in red. Okay. F of c plus delta x minus f of c over delta x. This is the slope of a secant line in calculus. Again, this is called the difference quotient. Now, I just want to point out to you that even though this looks strange to you, it absolutely makes sense from our slope of a secant line above. Let's take a look. Let's look at the denominator first at delta x here. Delta x is simply a change in x. And in our slope of our secant line, isn't x2 minus x1 a change in x? That's all that's going on here. Let's take a look at the numerator, the difference quotient. Let's look on the right of the minus sign, f of c. Isn't it true if you put a constant into a function that you get a y value out? And that's all this is. F of c is just our way in calculus of saying y1. Of course, the minus sign is matching. The first part on the left of the numerator is what throws students. And let's talk about this. Take a look here. Isn't it true if you take f of c, and c is an x value, and you make a small change in x? So in other words, if you have an x of c, and then you move a little bit, don't you have a new x? And when you put the new x into the function, you're going to get a new y, a y2. So this is the slope formula that you see above. It's just how we write it in calculus. Okay, but here we go. But isn't this slope that we have above just really an average rate of change? Or speed, if you will, an average rate of change. What if we made the 2 points in the picture above get infinitely close to each other? So, what if we made our 2 points get infinitely close to each other? To be more accurate. All right, I'm going to go on to the next page. So, isn't this slope really just an average rate of change? What if we made our 2 points get infinitely close to each other to be more accurate? So I'm going to draw a couple pictures of that. So take a look at the secant line, right, with the 2 points here, and let's just do that. Let's say that here's my curve again, right? And what if I made those 2 points get closer to each other? What if, here's my curve again, I made those 2 points get even closer to each other? And one last time, what if I made these 2 points get so close to each other that it almost looked like 1 point? In other words, we need a limit to do this. Of course, that's why it's in this section. We need a limit to do this. What does this look like? let's go back, and I'm just going to write again because we're on a new page, the difference quotient. Here was the difference quotient that we had written and talked about how it is actually the slope formula. Here it is. So what I'm saying here is, let's add a limit onto this. Aren't I saying that these 2 points are getting infinitely close to each other? So that would mean, look in the denominator here, that the rate of change, that delta x, the difference between the x's, the change in x, is approaching 0. So I'm going to put in front the limit as delta x approaches 0. So here's our difference quotient, but if we add the limit as delta x approaches 0, now this is the slope at almost 1 point. Okay, and this is called in calculus a derivative. It's a great thought, because what if you have a particle that's moving incredibly fast? An average rate of speed, right, in the position for that particle would not closely approximate how fast it's actually moving at 1 point. So at high rates of speed, it really does make sense to have a slope at 1 point for accuracy. Now, let's do some examples. Here is what your book asks for you. So on 2A, here's what we're going to do each time. They are asking us for each function, I have 3 different functions, to find the limit as delta x approaches 0 of the difference quotient. Now, you're going to see I changed it just a little bit for good reason. They write it a few ways in your book. So take a look here. Notice where there were C's that I have an X, because here's what we're going to do. They're not going to give us an actual C value for X. They are going to give us a function and ask us to use the difference quotient or find the derivative. So here's what's going to happen. We are going to be provided with a function. We're going to put it on the top right of this limit. We are then, notice where this X is in the function? We are going to substitute in x plus delta x on the left side of the numerator. Isn't that what is happening here? Take a look at this x in the function. Aren't we then going to substitute in x plus delta x into that function? We are going to keep our delta x in the denominator, and then we are going to try to evaluate the limit as delta x approaches 0. Okay, here's our first function. On 2A, f of x equals 5x plus 5. They are giving us this function and asking us to execute this limit. And what this should do is produce a derivative, a slope at 1 point. Now take a look at our line here though. We know the slope of this line. The slope of this line is 5. And so the reason why I picked this function first is because we know what our outcome should be when we do this limit. We should get a 5. So let's go ahead and do this. Now I do my limit in a particular way, easy to hard. I say, let's go ahead. The limit as delta x approaches 0, easy. I then write the denominator because it's just delta x, easy. The next thing I do in the numerator is put the minus sign. The next thing I do is I fill in the function on the right of the numerator because they gave it to me. There it is. Now you have to be careful. This entire function is being subtracted. And so that's what I'm going to do. I am going to put the function in parentheses. The entire function needs to be subtracted. Now, to the left. This is what throws students. If this throws you right here, don't worry, I will clear it up for you. What we're going to do is take the function here, and wherever we see in x, we are going to substitute in x plus delta x. Here I go. Here's my function. I'm going to write a 5. See this x here? Wherever I see an x, I'm going to replace it with x plus delta x. Don't forget your plus 6. Okay, now what we need to do is we have some algebra to do in the numerator. Notice, of course, if you try to evaluate this limit by direct substitution, you cannot, right? If delta x is approaching 0, we cannot put a 0 into this denominator, right? This is going to happen every time. So this means I need to do some algebra so this delta x eliminates, because I know what the slope is. It's 5. Let's do some math in the numerator. The limit is delta x approaches 0. Okay, here we go. I'm going to distribute the 5 to the x and the delta x. Don't forget your plus 6. And I am going to distribute the minus sign to the 5x and the plus 6. All right, still a little bit more cleaning up to do in the numerator. Notice here that your plus 6 minus 6 cancels out. Also notice that your 5x minus 5x cancels out. Notice in the numerator, you are left with 5 delta x divided by delta x, and those delta x's cancel, and you're left with the 5 that you knew was supposed to be the answer. Isn't that really cool? Let's try another example. So this is a 2b. And let's try a new function. Again, we are being asked to find the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. This time, the function that they're giving us is going to be something you're used to, f of x equals x squared. There we go. Let's just draw a little picture of that for ourselves, just to remind ourselves. 1, 2. There we go. Just drawing a little picture for myself. I'm going to refer to it later. Obviously, that's why I'm drawing it. Okay, let's go ahead. Let's substitute the function into our difference quotient. I always write the limit. I always do the denominator next. I always put a minus sign in my numerator, and I always put the function first on the left. Right, that would be the right-hand side, because it's so easy. They gave it to me, it's x squared. On the left of the denominator, notice wherever I see an x, I'm going to substitute in x plus delta x into the function. So, here we go. My function is x squared. This means instead of having an x in here, I have to substitute x plus delta x. Now, my saying in calculus is that it's not the calculus, people, it's the algebra. So let's go ahead and work this out. Obviously, I cannot solve this limit by direct substitution because I cannot put a 0 into the denominator. We have some work to do here in the numerator. Now, notice x plus delta x squared, I am going to write out in this way. Notice this is still x plus delta x squared, because I am going to do first, outer, inner, last very carefully here. So I get my terms correct. Okay, here we go. I'm going to do that in blue. First is x squared. On the outside, I have x times delta x. Now, what I do is I always put x delta x. I do not put delta x times x because then it looks like these two x's are next to each other. These are two separate variables. X and delta x are separate variables. It's almost like an x times y. So again, I do not write delta x times x because it almost looks like I have an x squared when I do not. Notice on the inside, I have the same thing. I have an x delta x, and last, I have delta x times delta x. That really is a delta x squared. Now don't forget minus x squared. and there's my denominator. We obviously have some little bit of work to do in the numerator. The limit as delta x approaches 0. All right, let's take a look in a different color what we have. Let's use red. Notice that the x squared and the minus x squared cancel. Notice I have 2 of these x times delta x's. There's one here and one here. I have 2 of those. And then a plus delta x squared. And my denominator is still delta x. Now, notice what is happening here. I still can't use direct substitution, right? I can't put a 0 into the denominator. But take a look. Do you see that in the numerator, each term has 1 delta x or more, and in the denominator? Okay, so what I'm going to do is, you can do this without doing extra work, but I'm just going to show you by splitting it up. This delta x is a common denominator, so I am going to rewrite this expression as 2 separate fractions. I just want to make sure you don't mess up your algebra. Okay, the limit as delta x approaches 0. I can see now, because I split up the 2 fractions, that these delta x's canceled, and I am left with 2x in the first fraction, and 1 delta x cancels 1 delta x from this fraction and leaves 1 in the numerator. Notice my denominator is canceled, so I can now use direct substitution to evaluate the limit, and I'm going to put a 0 in for delta x, and my final answer is 2x. I know you were probably expecting a fraction, you know, or a value here, but we get an answer of 2x. What does this mean? We will talk about this more in class, but here's what it means. When you have the function x squared, there is a slope function associated with it, and it is 2x. In other words, for any x on x squared, when you put it into this difference quotient, this slope function, it will give you the slope on x squared at that x. Let's try it. Here's our slope function. When we evaluate it at x equals 0, we get 0 out. And take a look, where x is 0, if I drew a tangent line, it would have a slope of 0. How about at x equals 1? Where x equals 1, 2 times 1 is 2. Let's take a look. Let's go to where x is 1. That's right here. And if I drew a line, right, that shows that slope at that one point, it could very well have a slope of 2. This function seems to be working as a slope function for any x of x squared. Let's try at x equals -1. Notice when I put it -1 into the slope function, I get a -2. Let's go to the graph. When x is -1, on the graph, if I drew a line right at that point to show the slope at a point, that definitely could be a slope of -2. Okay, let's try one more function. So let's try, this is 2c. Again, we are doing the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. And this time we're going to make our function 1 over x. Again, it is not the calculus, it is the algebra. Here we go. The limit as delta x approaches 0, delta x is in the denominator, and in the numerator, my function is 1 over x, and on the left side of the numerator, wherever I see an x in the function, I am going to replace it with x plus delta x. There we go. And so obviously we can't use direct substitution to solve this limit because we cannot put a 0 in for delta x. So we are going to have to do some algebra with the numerator. We'll take a look here. We are trying to subtract two fractions that do not have a common denominator. So I'm going to have to make one. Here we go. Notice in this second fraction, I am missing in the denominator an x plus delta x. So I am going to multiply the denominator by x plus delta x. This means I also have to multiply the numerator. There we go. In the first fraction, I am missing a factor of x. So I am going to multiply the top and the bottom by x. This is looking pretty crazy. Let's keep going. The limit as delta x approaches 0. Now hang out with me here. Here's my denominator. Now take a look. In my numerator, notice I now have a common denominator. I am going to put my minus sign and I am going to write the common denominator that I now have. X times x plus delta x. X times x plus delta x. Now I'm going to write my new numerators. My numerator, in the numerator is x times 1 is x, and here is x plus delta x. Okay, we obviously have a common denominator in the numerator. Let's bring that together as one fraction. Again, I'm going to have you watch super carefully here in the numerator. Okay, here is my common denominator in the numerator. Now let's do the math in the numerator, x minus this numerator. You have to be super careful. This minus means the entire numerator that I am pointing at here needs to be subtracted. That would be x minus x minus delta x. Okay, now, well, this looks ugly, right? I still have a delta x in the denominator. Okay, here's what I'm going to do. Putting delta x over 1. Do you also see in the numerator where I'm pointing here that x minus x cancels? That's nice. But this is still an ugly expression. I have one one fraction divided by another. Let's go ahead. We know what to do when we have one fraction divided by another. We keep the first fraction. Here we go. And we multiply by the reciprocal. This is really cool because take a look now. Now, my delta x cancels here and here. Do not lose this negative. Okay, now notice, sure there's a delta x in the denominator, but when I substitute in a 0 right here, it doesn't make the whole denominator 0. So let's take a look. In the numerator, I have a negative 1, and in the denominator, this becomes 0, and I have x times x is x squared. And here is our final answer. What does this mean? Negative 1 over x squared. It means that if you graph the function 1 over x, the rational expression, you know what it looks like. It means that for any x on this original function, that its slope function is x squared. In other words, notice where x is 1, if I put a 1 into the slope function, I get a negative 1 out. Notice when I go to where x is 1 on the function and I draw a tangent line, that slope really does seem to be a negative 1. Let's check where at x equals negative 1. Notice when I put a negative 1 in and square it, I still get a negative 1 out for the slope. And when you take a look at this function where x is -1 and you draw a tangent line, it does have a slope of -1. So thank you for hanging out with me. Here is an actual picture of the notes that I was looking at, but I didn't have anyone to help me with. And I hope you have a fantastic day.